In this video, we're going to be continuing to talk about how we can figure out the rate law for an overall reaction based on its mechanism. But in this one, we're going to be looking at how we do that when it's not the first step, that is the rate determining step. So the reason why that presents a difficulty for us is that a rate law should always be expressed in terms of the reactants for a reaction. Sometimes they'll also include catalysts, sometimes they'll also include products, but the one thing that we should not include wherever possible is intermediates. And if we look at an example like the one I have here, where the second step of our mechanism is the slow step. So just like before, that means that the rate law for our overall reaction is going to be governed by that slow step. So if we write the rate law for the slow step in this mechanism, which is step 2, we know the steps in a mechanism are elementary, so we can take the reaction orders with respect to B and C, just based on their coefficients, which are 1. So the rate for step 2 would be equal to the rate constant for this step times the concentration of B times the concentration of C. But if we look at what these things are, in our reaction, B only ever appears on the left, which means it's a reactant. So that one's fine. But C is a product of step 1, and then it is consumed in step 2. So C is an intermediate. So we have an intermediate present in the rate law of our rate determining step, but that can't appear in the rate law of our overall reaction. So that means that we can't just take this rate law exactly as it is. We need to find some other equivalent expression. So we need to replace this to get our overall rate law. So what we're going to do is use step 1 to our advantage here. This particular intermediate was created in step 1. So if we take a look at that, we see that this step is faster, and it is also important that is an equilibrium process. So reaching equilibrium, because that step is fast and it is establishing equilibrium, we can assume at any given moment that it's pretty much at equilibrium. So the rate for step 1, I'm going to put down here, and we will see why in a moment. The rate for step 1, as it is written, we have 1 molecule of A, 1 molecule of B. So it's going to be first order with respect to each of those. Now, because this is in equilibrium, it is a reversible process, we can think about the rates for both the forward and reverse direction, since it's going both ways. So what we just wrote here was the rate for the forward reaction. The rate of the reverse reaction, I'm going to label it rate -1 for step 1, but going backwards, is going to have a different K. And in reverse, C becomes a reactant. So this is going to be in terms of C. Coefficient of 1. So it is first order. So we can write the rate laws for both the forward and reverse reactions. And when something is at equilibrium, what it means for something to be equilibrium, the definition of something at equilibrium, is that the rate of the forward reaction is equal to the rate of the reverse reaction. So we talk about this in Chem 2. But you haven't really learned about rates yet, so it doesn't have a lot of meaning. But now we can actually express this mathematically, that if the rate of the forward reaction for step 1 is equal to the rate of reverse, that means that rate 1, as we have them labeled, is equal to rate minus 1. So I can say that this expression is equal to this expression. So K1 times the concentration of A times the concentration of B is equal to K minus 1 times the concentration of C. So you may see where I'm going with this. The thing that we're looking to replace is concentration of C. So ultimately, our overall rate law is still going to be based on this rate law that we wrote for step 2. We just have to replace that intermediate with something else, with reactants or products or catalysts, because those are concentrations that we're better able to control, is why we want the rate law in terms of those things. The concentration of intermediate just kind of is what it is, and we can't really do much about it. Whereas especially reactants and catalysts, we can directly control the reaction, the concentration that we put into our system of those things. So it's more useful to have a rate law in terms of those things. So we see that concentration of C is appearing in these rate laws related to step 1. So we now have this expression that a constant times the concentration of C is equal to different concentration times the concentrations, different constant times the concentrations of A and B. So all we're doing here is solving this for C, K1 over K minus 1 times A times B. And now we can plug this whole expression back into our rate law for our rate determining step to get our overall rate law. A and B are both reactants in this process. So if we're replacing C with those things, we'll be good to go. So our overall rate law here, the different K's, we end up with a constant times a constant over a constant, just end up collapsed into a new constant. So those all kind of just get sucked in together into one shiny new K. And then we have the concentration of B, and we're replacing the concentration of C with A times B. So we can simplify this. We've got B times B here. So the best way to express this would be that our rate is equal to K times concentration of A times B squared. So we just have to do a little bit of extra work to figure out what we replace our intermediate with. Generally speaking, if you look at your mechanism, for the purposes of the AP exam, it will either be the first step slow or the second step slow. If it is farther on in the mechanism, it's the same process. It's just often more time consuming because you may have to go through multiple replacements like this. But it's fundamentally the same. So they'll only ever give you first or second step slow just for the sake of time. So what you should find is that if you have an intermediate in your rate law, it's the product of the first step, you're going to end up replacing that intermediate with the reactants of the first step. Is kind of the shortcut version of this to get to your final overall rate law.